There are two polar vortices in the atmosphere of planet Earth, one around the North Pole, and one around the South Pole. Each polar vortex is a persistent, large-scale cyclone, circling the planet's geographical poles. The bases of the two polar vortices are located in the middle and upper troposphere and extend into the stratosphere. They surround the polar highs and lie in the wake of the polar front. These cold core low-pressure areas strengthen in the winter and weaken in the summer due to their dependence upon the temperature differential between the equator and the poles. They usually span less than 1,000 kilometers in diameter, within which the air circulates in a counter-clockwise fashion in the Northern Hemisphere, and in a clockwise fashion in the Southern Hemisphere. As with other cyclones, their rotation is caused by the Coriolis effect. The Northern Hemisphere vortex often contains two low-pressure centers, one near Baffin Island, Canada, and the other over northeast Siberia. Within the Antarctic vortex in the Southern Hemisphere, a single low-pressure zone tends to be located near the edge of the Ross Ice Shelf near 160 west longitude. When the polar vortex is strong, the westerlies increase in strength. When the polar cyclone is weak, the general flow pattern across mid-latitudes buckles and significant cold outbreaks occur. Ozone depletion occurs within the polar vortices, particularly over the Southern Hemisphere, reaching a maximum depletion in the spring. History: the polar vortex was first described as early as 1853. The phenomenon southern stratospheric warming appears during the winter in the Northern Hemisphere and was discovered in 1952 with radio sonde observations at altitudes higher than 20 kilometers. Identification: polar cyclones are climatological features that hover near the poles year-round. The stratospheric polar vortex develops poleward and above the subtropical jet stream. Since polar vortices exist from the stratosphere downward into the mid-troposphere, a variety of heights pressure levels within the atmosphere can be checked for its existence. Within the stratosphere, strategies such as the use of the 4 megabytes pressure surface, which correlates to the 1200 K isentropic surface, located midway up the stratosphere, is used to create climatologies of the feature. Due to model data unreliability, other techniques use the 50 megabytes pressure surface to identify its stratospheric location. At the level of the tropopause, the extent of closed contours of potential temperature can be used to determine its strength. Horizontally, most polar vortices have a radius of less than 1,000 kilometers. Others have used levels down to the 500 hectopascals pressure level above sea level during the winter, to identify the polar vortex. Duration and power: polar vortices are weaker during summer and strongest during winter. Individual vortices can persist for more than a month. Extratropical cyclones that occlude and migrate into higher latitudes create cold core lows within the polar vortex. Volcanic eruptions in the tropics lead to a stronger polar vortex during the winter for as long as 2 years afterwards. The strength and position of the cyclone shapes the flow pattern across the hemisphere of its influence. An index which is used in the Northern Hemisphere to gauge its magnitude is the Arctic oscillation. The Arctic vortex is elongated in shape, with two centers, one normally located over Baffin Island in Canada and the other over northeast Siberia. Around the North Pole, the Arctic vortex spins counterclockwise with wind speeds of 80 miles per hour, stronger than the jet stream's normal 70 miles per hour winds. In rare events, when the general flow pattern is amplified, the vortex can push farther south as a result of axis interruption, such as during the winter 1985 Arctic outbreak. The Antarctic polar vortex is more pronounced and persistent than the Arctic one. This is because the distribution of land masses at high latitudes in the Northern Hemisphere gives rise to Rossby waves which contribute to the breakdown of the vortex, whereas in the Southern Hemisphere the vortex remains less disturbed. The breakdown of the polar vortex is an extreme event known as a sudden stratospheric warming. Here the vortex completely breaks down and an associated warming of 30–50 degrees Celsius over a few days can occur. The formation of the polar vortex is primarily influenced by the movement of wind and transfer of heat in the polar region. In the autumn, the circumpolar winds increase in speed, causing the polar vortex to spin up further into the stratosphere and the values of potential vorticity to heighten, forming a coherent air mass, The polar vortex. As the winter comes, the winds around the poles decrease, and the air in the vortex core cools. The movement of the air becomes slow, and the vortex stops growing. Once late winter and early spring approach, heat and wind circulation return, causing the vortex to shrink. During the final warming, or the late winter, large fragments of the vortex air are drawn out into narrow pieces into lower latitudes. In the bottom level of the stratosphere, strong potential vorticity gradients remain, and the majority of air molecules remain confined into December in the Southern Hemisphere and April in the Northern Hemisphere, well after the breakup of the vortex in the mid-stratosphere. The breakup of the polar vortex occurs between middle March to middle May, the average date being April 10. This event signifies the transition from winter to spring, and its impacts on the hydrological cycle, growing seasons of vegetation, and overall ecosystem productivity. The timing of the transition also influences differences in sea ice, ozone, air temperature, and cloudiness. Early and late polar breakup episodes have occurred, due to variations in the stratospheric flow structure and upward spreading of planetary waves from the troposphere. As a result of increased waves into the vortex experiences higher amounts of heat sooner than the normal warming period, resulting in a faster season transition from winter to summer. As for late breakups, the waves dismantle the vortex later than normal, causing a delay in the season transition. The early breakup years are also characterized with persistence of remnants of the vortex, while the late breaking years have a quick disappearance of these remnants. In the early breakup phases, only one warming period occurs from late February to middle March, contrasting to the two warming periods that the late breakup phases have in January and March. Zonal mean temperature, wind, and geopotential height exert varying deviations from their normal values before and after early breakups, while the deviations remain constant before and after late breakups. Scientists are connecting a delay in the Arctic vortex breakup with a reduction of planetary wave activities, few stratospheric sudden warming events, and depletion of ozone. Sudden stratospheric warming events, when temperatures within the stratosphere warm dramatically over a short time, are associated with weaker polar vortices. This warming of stratospheric air can cause the direction of circulation in the Arctic polar vortex to go from counterclockwise to clockwise. These changes are loft force changes below in the troposphere. An example of an effect on the troposphere is the change in speed of the Atlantic Ocean's circulation pattern. A soft spot just south of Greenland is where the initial step of downwelling occurs, nicknamed the Achilles heel of the North Atlantic. Small amounts of heating or cooling traveling from the polar vortex can trigger or delay downwelling, causing circulation of heat through the Atlantic Ocean currents to be stopped or sped up. Since all other oceans depend on the Atlantic Ocean for the transmission of heat and energy, climates across the planet can change dramatically. The weakening or strengthening of the polar vortex can alter the sea's circulation more than 1 mile below the waves. Strengthening storm systems within the troposphere can act to intensify the polar vortex by significantly cooling the poles. La Niña plus or minus or Euro-related climate anomalies tend to favor significant strengthening of the polar vortex. Intensification of the polar vortex is also associated with changes in relative humidity as downward intrusions of dry, stratospheric air enter into the vortex core. With the strengthening of the vortex comes a long-wave cooling due to a decrease in water vapor concentration near the vortex. The decreased water content is a result of a lower tropopause within the inside of the vortex, which places dry stratospheric air above moist tropospheric air. Instability is caused when the vortex tube, the line of concentrated vorticity, is displaced. When this occurs, the vortex rings become more unstable and prone to shifting by planetary waves. The planetary wave activity in both hemispheres varies year to year, producing a corresponding response in the strength and temperature of the polar vortex. The number of waves around the perimeter of the vortex are related to the core size. As the vortex core decreases, the number of waves increase. The degree of the mixing of polar and mid-latitude air depends on the evolution and position of the polar night jet. In general, The combination of these two remains small inside the vortex compared to the outside. Mixing occurs with unstable planetary waves that are characteristic of the middle and upper stratosphere in winter. Prior to vortex breakdown, there is little transport of air out of the Arctic polar vortex due to strong barriers exist above 420 kilometers. Below this barrier exists the polar night jet, which is weak in the early winter, so any descending polar air mixes with the mid-latitudes. In the late winter, air parcels do not descend as much, causing mixing to be less frequent. After the vortex is broken up, the ex-vortex air is dispersed into the middle latitudes within a month. Sometimes, a piece of the polar vortex can be broken off before the end of the final warming period. If large enough, the piece can plunge over Canada and the Midwestern, Central, Southern, and Northeastern United States. This diversion of the polar vortex can occur due to the displacement of the polar jet stream, such as the significant northwestern push of the polar jet stream over the western part of the United States in the winter of 2013–2014. Occasionally, the high-pressure Greenland block can cause the low-pressure polar vortex to divert to the south instead of sweeping across the North Atlantic. Climate change. A study in 2001 found that stratospheric circulation can have anomalous effects on weather regimes. In the same year, researchers found a statistical correlation between weak polar vortex and outbreaks of severe cold in the Northern Hemisphere. In more recent years, scientists identified interactions with Arctic sea ice decline, reduced snow cover, evapotranspiration patterns, NAO anomalies or weather anomalies which are linked to the polar vortex and jet stream configuration. However, because the specific observations are considered short-term observations, there is considerable uncertainty in the conclusions. Climatology observations require several decades to definitively distinguish natural variability from climate trends. The general assumption is that reduced snow cover and sea ice reflect less sunlight and therefore evaporation and transpiration increases, which in turn alters the pressure and temperature gradient of the polar vortex, causing it to weaken or collapse. This becomes apparent when the jet stream amplitude increases over the Northern Hemisphere, causing Rossby waves to propagate farther to the south or north, which in turn transports warmer air to the North Pole and polar air into lower latitudes. The jet stream amplitude increases with a weaker polar vortex, hence increases the chance for weather systems to become blocked. A recent blocking event emerged when a high pressure over Greenland steered Hurricane Sandy into the northern mid-Atlantic states. Ozone depletion. The chemistry of the Antarctic polar vortex has created severe ozone depletion. The nitric acid in polar stratospheric clouds reacts with chlorofluorocarbons to form chlorine, which catalyzes the photochemical destruction of ozone. Chlorine concentrations build up during the polar winter, and the consequent ozone destruction is greatest when the sunlight returns in spring. These clouds can only form at temperatures below about 80 degrees Celsius. Since there is greater air exchange between the Arctic and the mid-latitudes, ozone depletion at the North Pole is much less severe than at the south. Accordingly, the seasonal reduction of ozone levels over the Arctic is usually characterized as an ozone dent, whereas the more severe ozone depletion over the Antarctic is considered an ozone hole. This said, chemical ozone destruction in the 2011 Arctic polar vortex attained, for the first time, a level clearly identifiable as an Arctic ozone hole. Outside Earth. Other astronomical bodies are also known to have polar vortices, including Venus, Mars, Jupiter, Saturn, and Saturn's moon Titan. Hot polar vortex equals, Saturn's south pole is the only known hot polar vortex in the Solar System. See also, Polar amplification, weather portal. References. Further reading, Nash, Eric R. Newman, Paul A. Rosenfield, Joan E. Schoebel, Marker and objective determination of the polar vortex using Ertl's potential vorticity. Journal of Geophysical Research 101, 9471 8. Bibcode, 1996 JGR. 101.9471 ENDOI, 10.1029/96JD00066. Buttkart, Neil. Remsburg, Ellis E. The area of the stratospheric polar vortex as a diagnostic for tracer transport on an isentropic surface. Journal of the Atmospheric Sciences 43, 1319 Euro 39. Bibcode, 1986 Chat S. 43.1319 doi, 10.1175 over 1520-0469, 1986, 0432.0 co. 2. Schoebel, Mark R. Late, Leslie R. Newman, Paul A. Rosenfield, Joan E. The Structure of the Polar Vortex. Journal of Geophysical Research 97, 7859 Euro 82. Bibcode, 1992 JGR, 97.7859 S doi, 10.1029/91 JDO2168. Coy, Lawrence. Nash, Eric R. Newman, Polar Meteorology of the Polar Vortex, Spring 1997. Geophysical Research Letters 24, 2693 Euro 6. Bibcode, 1997 GORL 24.2693 doi, 10.1029/97 gallons 52832. Schoebel, M.R. Hartmann, D.L. The Dynamics of the Stratospheric Polar Vortex and its Relation to Springtime Ozone Depletions. Science 251, 46 Euro 52. Bibcode, 1991 Sci. 251. 46 S doi, 10.1126/Science. 251.4989.46. PMID 17,778,600 External links, Archive of Northern and Southern Hemisphere blocking events. Global Climate Change Group. Retrieved January 7, 2014. Polar Vortex. Environmental Terminology and Discovery Service. Retrieved January 6, 2014. World Temperature Gradient. Integrated Publishing, Aerographer Meteorology. Retrieved January 29, 2005. The Antarctic Polar Vortex. Dynamics in the Ocean and Atmosphere. Retrieved January 29, 2005. The Polar Vortex and Arctic Weather Patterns. Arctic Climatology and Meteorology. National Snow and Ice Data Center. Retrieved January 29, 2005. NASA sees into the eye of a monster storm on Saturn. Cassini-Huygens, News Press Releases 2006. Retrieved November 12, 2006.